The PLC Professor website and YouTube channel would like to present RS Logix 5000 Jumpstart. We're beginning with RS Logix 5000 opened and without a project. We're going to start by going through the very basic steps of creating a project and creating a hardware image. So the first thing we want to do is we want to switch focus for Windows onto RS Logix 5000. You see the title bar is grayed out now. If I click on it, it turns blue. So the focus is now within my screen is on RS Logix 5000. So I'm going to click on File, New, and we already have an L35E processor up there. That's the processor that I have today to use. But if we were to open up this drop down list and scroll up and down the list, you'd see that there's all the processors are there. So I'm going to pick an L35E. The firmware revision level of that processor is version 20. If you have a processor with version 17, then you have to use RS Logix version 17. So the firmware level of the processor and the rev level of the software have to match. We also need to give it a title, and I'll just call it My CPX, My Compact Logix. Now, we're going to create this project in a folder. Now, looking down here, Create In, I could put it there, but that was a previous project. So I'm going to browse, and I'm going to go up to Desktop, and click on Desktop. So I'm actually going to put this project right on the desktop to make it easy to find. So notice the path there has changed. If I wanted to, I could create a folder and put it in there. So for right now, we'll just put it on the desktop. Click OK, and the geeks are in the background creating your project for you. All of the file structures and folders, and there it is. Now, we're not going to go through all of these. I will mention a couple things though that will change. Right now, that is your hardware image right there, and basically that is the 1769 L35E plugged into a backplane. So it has a local bus. They don't really call it a backplane, they call it a bus. A I/O chassis has a backplane, which is the circuit board that goes the full length of the back of the chassis that has connectors on it, and when you slide I/O modules into the chassis, they slide into the connectors that are on the backplane. Compact Logix has a bus, meaning that the actual backplane, if you want to call it that, is part of the I/O module. So as you put these I/O modules together, there's a ribbon cable, and you are actually extending that backplane or that bus from module to module through the module. There's not actually a separate backplane. Also, we're going to point out that for controller tags, we'll double click on that and you see there's nothing there. Okay, right now there are no controller tags. I'm going to go up and I'm going to close the controller tags. Then I'm going to open up the main program and double click on program tags, and you see there's no program tags. One other place I want to point to is module defined. There's no plus sign next to module defined, so there are no module defined data types. These are all of the data types. And you're saying, well, what's a data type? Well, a timer data type with a preset accumulate and control bits, counter data type with preset accumulate and control bits. There's integers, double integers. They are data types, and that's a lecture for another day. But I want to point out that there are no module defined data types right now. See, there's no plus sign. Later on, we'll go back and look at this again. So first thing we want to do is we want to add an input module. So we go to the Compact Bus Local, where you right click, new module, and we have an IQ16, so I type in IQ, and since it's a 1769 bus, it eliminates everything but 1769 part numbers to begin with, and now I have all of the part numbers beginning with IQ. So right there's ours. I can double click on it or move that up where you can see it. I can click on that one and go down to the bottom and click on create, and then we need to give it a name, DC inputs. And if you want to remind yourself what slot it's in, you can always put a 1 after it so you know it's in slot 1, as you can see here. If you needed to change the firmware level, that can be done right here. But for our simple jump start, we just select the module, give it a name, make sure it's in the right slot, and click OK. Close that. We come back, and now we see we have a 16-point DC sync source card added. So our hardware image now has been expanded to include an L35E and an input card. So now if we go up to module define, I'm going to expand this. Remember, there was no plus sign here before. Now I have a module defined data type. So if I double click on that, open it up, and you see I have an integer for my data bits, and for my fault bits I have a double integer. That's 32 bits. Now this is a template. You see it's all grayed out. So it's there for you to refer to, but you don't use it for anything. But it has to be in here, otherwise RSLogix 5000 does not know what to assign in memory to represent that card. To further illustrate that, let's add another card. Right click on your Compact Bus Local, new module. Now we want to add an OB16. So I type in OB, there it is right on top, 1769 OB16. I'll just double click on it, and we'll call it DC outputs. And it's in slot 2. You don't have to put 2 on there. As a matter of fact, you could call this anything you want. You could call that first module Monkey Business and this one Shenanigans. So once in a while I think about doing that just to prove the point. So you're just putting a name in there that will help you when you're looking at your code to remind you what you're looking at. So we name it, verify the right slot number, and we click OK. Then we close the module creation box. Now look, we have an input card and an output card. Now look what's happened to our module define. We've added 3 more data types. So this is for configuration. This is information that comes from the output card. That's right, you heard me right. This output card actually supplies information to the processor, and then of course the output. So in terms of conventional thinking, this would be the data type for the input states, and this is the data type for the output state. So if I double click on this one, you see that there's lots of stuff in there, and we're not going to talk about it because I promised you a jump start. Click on inputs. This is the information that comes back from the output module, and then of course this is the actual data, which is an integer 16 bits. So we'll close those down, but I wanted you to see these module defined data types start populating this area as you add modules. Okay, so this is our hardware image. Now I'm going to switch over to RSLogix 500 to illustrate a point about the data table. Notice with 5000 that you don't have B3, T4, C5, R6, N7, F8, or any of that. There is no data table right now. Here's your controller tags. There's your input cards you just added. There's local slot 1 I, local slot 2 configuration, input and output. So these three tags right here represent that module in slot 2. This single tag represents the module in slot 1. If I expand that, then expand the data, this is input 0, input 1, input 2, and so forth. And if I expand this tag, that's output 0, output 1, output 2, and so forth. So in our controller tags, in the Logix family, the data table's split into two areas: controller tags and data tags. With SLC 500 or PLC5 MicroLogix, you only have one data table. Now there's a reason for this. That's because in 5000 you can have multiple programs. I just expanded the main task, the main program, the main routine, and program tags. If I double click here, you see there's no tags yet. So there's no database in the program tags, but there is in the controller tags. These two were all one in the older products. The reason it's been split out is because in the Logix engine you can have more than one task, and in each task you can have more than one program. So a program is what you had in a SLC 500 or a MicroLogix. So a MicroLogix had one program. In the Logix products, ControlLogix, CompactLogix, etc., you can have up to 100 completely separate unique programs in a task, and you can have more than one task. Now these numbers vary a little bit from processor to processor. The point is, in the Logix engine you can have more than one program, which means that you have to separate the program tags out to the program, because each program has its own data table. Just like if you had 3 MicroLogix processors, they each have their own database. But you could include the I/O in that database because there was only one database. In this product, because you can have more than one program, you have to split up the database into controller tags, which is the I/O and anything you want to put in there. You can put everything in that one database, but because you can have different programs, they allow you to create separate databases for each program. Hence, program tags, controller tags. All I/O, though, will always go into the controller tags. Now let's jump over to 500, RSLogix 500, and I want to show you something. This should be familiar to most of you. By the way, if you're not familiar with a PLC at all, you're in the wrong video. There are many other videos on YouTube that you can watch that introduce you to a PLC, and most of them are based on the older products that program with RSLogix 500, but it is a good place to learn. This is not a good starting point if you're just starting. So this is RSLogix 500 Pro. I'm going to create a project, File, New, and I'll pick a 64K 505. That's a good one. Okay, notice that I automatically get a set of data files beginning with output file, input file. Notice 0, 1, 2, 3, 4, 5, 6, 7, 8. They're numerical in order. This is where your output image would be, your input image. This is the status for the processor. The status is not visible in RSLogix 5000. You have to do a get, use a get instruction, get system variable or set system variable if you want to work with the status in a ControlLogix or CompactLogix processor. But moving on, we have B3, T4, C5. So binary, timer, counter, control, integer, and float. So let's open up B3, and you see you have one word, one 16-bit word, or one integer. And this is not a memory location. I want to reiterate that. B3:0 is a pointer that points to a real memory location. You'll never know what that real memory location is. but B3:0 is a tag name, but it's numerical in its appearance. I'll show you what I mean here in a second. That gives you 116-bit word in file B3, but let's say you need more than that. You go to Properties, and you can either put the number of elements you want here or put the highest address. We'll just put in 10. We'll apply. Now look, you have 10 16-bit words. So I just expanded the array with the tag name B3 from 1 element to 10 elements. We'll close that and we'll go to timers. See, there's one timer there: enable, timer, timing bit, done bit, the base, preset, and accumulate. And if you had a description or symbol, it would be there. So this is one element, the first element in the timer array T4. So element 0 of T4. So I'll go to Properties and we'll make this, we'll just say 5. We want an array of 5 timers. Hit apply, OK, there you are. Timer array 4, T4, that's just a tag name. And this is all pre-done for you with the other products. We could go to floating point. See, you have one floating point word there. You have word 0 or element 0 of the array of floating point or real values F8. That's the name of the file, F8. And 0 is the element of that array. So if I want to increase that, I go to Properties and we'll put in 20. Now we have F80 through F819. Sounds like a new jet fighter. And of course, in these you can put in floating point values. Okay. So this is what you're used to. Single element arrays, and then you expand them, or you can create a new one. You can right click Data Files, New, and you can create, let's say you create any of these. Well, we'll just do another binary, and we'll let it be file 9, and we'll give it 12 elements. So see, now we have a B9. I didn't give it a name. I could have. If I double click, see, you have 12 elements, 0 through 11. So you had this kind of pre-configured data files with the products that RS Logix 500 programs. Now, if we go back to 5000, we don't have any of that. You have to create them all. So if you want to have the same look that you had with 500, you can do that. Now, to me, that's emotional baggage from the past, but we'll go ahead and do that. I'll show you how to do that. So we're in the program tags. I think I'll go in the controller tags and do this. So I'm going to click there. I'm in Edit Tags. Make sure you're in Edit Tags. I'm going to type in uppercase B3. Okay, then I'm going to go over to Data Type, and I'm going to pick integer, INT, and I'm going to give it an array size of 10. Then click anywhere outside of that, and then it finishes that. Now, see, I have B3. And just for grins, let's do a T4. So it looks more like SLC 500 Micrologics. Only this time, because it's a timer, I want a timer data type. And we'll do 5 just like we did with a SLC. And let's do an F8. F8. So that's my name, F8. I go here to data type, I type in RE to get real, and what I make that? 20. Okay, now I've got B3, T4, and F8. If I expand B3, I have B30, B31, B32. If I further expand that, I have B3, word 0, bit 0 through 15. Or let's expand B34. I have B3, word 4, data file B3, word 4, bit 0 through 15. For timers, I have T40 through T44. Expand one of them, I have preset, accumulate, enable, timer, timing, bit, and done bit. Now this looks identical to RS Logix 500, except in RS Logix 500 it would be T4:1.PRE. So we have brackets here instead of a colon and a decimal point. Those punctuation characters, if you want to call them that, are delimiters. They are what separate different pieces of your pointer or memory location. So other than the difference of not having a colon, or brackets here, having a colon, instead you got brackets surrounding the word, it pretty much looks the same. So what I just did here in creating B3, T4, and F8, in the other products that you program with RS Logix 500, it was done for you. But you remember, I created a B9. So if I did that here, I typed in B9, and then for data type INT, integer, and created, I think, 12 of them. Okay. See, B9, word 0 through 12, and they expand out to B9, word 1, bit 0, bit 1, bit 2, bit 3, bit 4, and so on. So I hope this helps you a little bit understand not just how you create the database and the data files in RS Logix 5000, but gives you a better understanding of what you used in the past with products that program with RS Logix 500. Now that we have a hardware image that includes the processor, an input and output module, let's download these and go online. So we go to communications up here, Who Active, we pick the processor, we click on download. We have a no guts, no glory message here. Read it once and then click on download. Yep, change it to the remote run mode. Okay, now we have the processor with a program in it and it's downloaded. So we'll go look at the controller tags, and you see they're kind of rearranged in alphabetical order, B, B, F, L's, and T. That's just normal. And then we'll look at the program tags. So you see we have none. Okay, the first thing people want to do is to create a rung of logic. So we'll go to the main routine under main program, double click, and you automatically get a new rung if it's an empty subroutine. I'm going to delete that. Now I'm going to go up here and drag down a new rung just so you can see it happening. New rung. I want a true-if-on instruction and an output energize. So I'm going to go up here and I'm going to call this my push button. Okay, it's just a name. Now I'm going to go over here and I'll call this my indicator. Now you see the ease. The rung is still in the edit mode, and if we put a mouse over undefined tag, my push button, over here undefined tag, my indicator. So we go here, we right click, we say new. Now I'm going to leave this as an internal tag. I'm not going to alias it to an actual IO. We'll do that in a minute. So it's a base type instruction, and it's Boolean, and it's in the, as far as the tag scope, it's in the processor tags. We drop down the list, you see you have my CPX and main program. My CPX is the processor, main program is the program tags. We only have one program. So we'll leave it as a controller tag. We'll click create. Now when we mouse over, tag, my push button, data type, Boolean, scope, controller, value 0. Go over here, right click on that undefined tag, and we'll also leave that as a base Boolean and in the controller tags, and hit create. Now we see we have eyes. Now we're doing this online, okay? So if you do your edits online, that's okay. You have to be careful when creating tags, because once it thinks it's created, it won't let you change it online. You're going to have to go offline to change it. So we want to finalize this edit here. So we go to this button right here, finalize all edits in program. We click on that, read that message once, and click yes. Now we have a rung of logic, and we're in the run mode and everybody's happy. So I want to turn on that bit. So I right click. Remember, this is a true if on instruction. If this instruction is true, the whole rung is true, and it should turn on that bit. So I'm going to toggle this bit. You can see it's highlighted, meaning the instruction is true. It's not highlighted because the bit is on. It's highlighted because the instruction is true. If I were to take, I'll double click to put this in the edit mode, and I'll grab a true if off instruction, and I'm going to grab the address here and drag it over. Now I'm going to finalize my edits again. Okay, now I've got a true if on and a true if off addressing the same memory location. Remember, my push button is a tag name. It's a pointer that points to the actual memory location. My push button is not a memory location. It is a tag name that points to the memory location. You'll never know what the memory location is numerically. So I'm going to right click on this and turn that bit off. See, the other one's true. This is true because the bit is off. This is false because the bit is off. So remember, this is true if on, true if off. Well, with this configuration, that rung will never be true. So we'll go back and we'll put this in the edit mode by double clicking on the rung number. Select that, hit delete, and then finalize all edits. Now I'm going to toggle this on. See, now it's true. So we'll toggle it back off. Now, let's actually use I/O. Well, I've already created these tags, so if I go to edit them, in other words, right click on the tag, not the instruction, on the tag, edit my push button properties, notice that this is grayed out. I can't change it to an alias. So I click OK. Now, remember that when you are offline, everything that you're doing in RAM of your laptop and on the hard drive of your laptop, not in the PLC, not in the controller. If you're online, like we are right now, everything we've done is in the controller. So if you're working in the controller and you decide to go offline, make sure you save first. And it's going to ask you, online tag values may have changed. Because remember, you have a database, but then in the database you have values in all of those tag memory locations. If you want to have that offline, you have to save that, in other words, upload it before you go offline. Now you go offline. Okay, now we want to edit the push button and the indicator to be real I/O. So we right click, edit. Instead of base, we want alias 4, and this is an input, so we expand local slot 1 I, click on data, and then go over here to the drop down list and pick bit 0, and we hit apply. Okay, now look, my push button is an alias for this tag name that points to a memory location. Let's do the same here. Edit my indicator properties, pick alias, drop down the list, alias 4, local 2, O for output, data, drop down the bits and pick we'll just pick bit 0. Apply and OK. Now look, my push button is an alias for a tag that points to a memory location that will store the state of the push button or toggle switch attached to input 0 in slot 1. My indicator is a alias for a tag name or pointer that points to the state of bit 0 of the data word output wise of slot 2, which is your output card. So let's download this. Whoactive, download, download again, put it back in the run mode. Now I'm going to operate the toggle switch. Okay, turn it on, bit goes true, output goes on. Turn it off, bit goes off. This instruction is false, and it turns this bit in memory off. Now remember that the rung is true and false. From here over, this is true and false. This is on or off. So when you see this highlighted, that means that that bit is on. When you see this highlighted, that means that the instruction is true. Which, remember, if it was a true if off instead of true if on, it would be true when the bit in memory was off instead of on. So be careful what you're doing here. Okay, that's enough just to get us going for right now. We'll continue on later. There's one additional thing that I would like to mention. And very early in this presentation I mentioned rev levels, firmware levels. What I failed to mention was when you are configuring your I/O modules, you have to select electronic keying. So I'm going to open up the iQ16 and notice, remember I said you could change the firmware level here. You can also change the electronic keying. So if I click on that, you have a choice of exact match, compatible module, or disable keying. In this case, for the kind of labs that I'm doing, I always disable the keying. That way I don't have to concern myself with the revision level of the module. So you may want to disable the keying when you do your projects. And now we'll open up the output. Now notice the output is revision 2.1 where the input module was 1.1. And in this case we going to have to disable the keying because the compact logics that I have to work with that you can't see, it's hooked up to my laptop, those modules are 1.1, so this would be incompatible. So I picked disable keying. Now I will mention this just for your curiosity. Exact match means the major and minor rev level have to match. Compatible module means that the minor rev level does not have to match, but the major does. Disable keying, neither the major or the minor. See 2.1. 2 is the major, 0.1 is the minor. So you want to disable the keying. When it actually comes to a real project, you want them to match. You want an exact match because there's always the possibility that you've picked a module that has some features that were not supported by an earlier version. So if you have the newer version of the module with the newer firmware level, you want to pick exact match, because if you use that feature and you commission the project in the field on a machine or a process, and then a year later, 2 years later, whatever, bolt of lightning and the module is damaged, if they replace it with an incompatible module and you have disabled the keying, it will work, but those features that belong to the newer version will not work. Just a word to the wise. Thank you for watching.